Okay, so this is part two of the Z-transform review. So like the Laplace transform and the Fourier transform, the Z-transform has a lot of similar properties. It has, properties of linearity, it has properties of superposition. It has a lot of similar properties to the Fourier and Laplace transforms. And so one of these properties that is particularly useful is the time shifting property. And we can just illustrate that in this equation right here. It's very similar to the shifting property that you would see in the Laplace domain and the Fourier domain, where basically we're saying that if we take the Z-transform of, rather than x sub n minus k, where k represents a shift, that basically can be written as the transform of x of n multiplied by z to the minus k. So this z to the minus k, when it multiplies an expression, basically is having the effect of shifting each term by term in the expression by the amount that's in the exponent. The time shifting property is really easy to prove. What we do is realize that, first of all, here it is restated. In this particular example, we're using n sub 0 instead of k as our shifting variable. So this is just the time shifting property restated, and our range is the set of real numbers for n. So if we just take the Z-transform definition, and instead of plugging in x of n, we plug in x of n minus n0, then what we have to do is a change of variables. So we can define a new variable m as n minus n sub 0. So when we do that, our function then becomes x of m, and our z is raised to the nth power, which means it is raised to the m and n sub 0 powers. So we've just substituted for n in the exponent for z, and we've substituted for n minus n0 in the value for x, in the element for x. The sum here is taken from minus infinity to infinity. This proof was pulled from a mathematics course where the analogy was not being drawn to the Laplace transform. It was just a straight Z-transform, so the sum was going from negative infinity to infinity. In our data sets, because we're not operating on infinite data sets, we're operating on finite data sets, we usually have the shifted sum that starts with either 0 or 1, depending on how the computational system is working. So anyway, you can see from this sum that this portion of the sum right here, let's mark that, this portion of the sum right here is really just the Z-transform with a change of variable where we've got m instead of n. And then this term is just what got pulled out that does not represent the Z-transform. So we can take this portion of the sum and represent that as just the Z-transform of x. And then this term, remember n sub 0 is a constant, so it could actually be pulled out of the sum and then actually ends up over here multiplying the Z-transform variables. So the proof is very simple, like many proofs that you would do in the Laplace or Fourier analysis course. So what's an example of a Z-transform? Here's an example. We have a data set where we've just defined a data set x of n. It's has 6 elements. So if we wanted to take its Z-transform, then we would just take the first term, and that becomes the coefficient for z to the 0, which is 1. We take the second term, and that becomes the coefficient for z to the minus 1. The third term becomes the coefficient for z to the minus 2, and so on, noticing that each term represents a coefficient, and then we have, as we become more and more delayed, we have more negative powers of z. So that would be the Z-transform of this data set x sub n. Now, one of the reasons that we want to work in Z-space as opposed to sample space is the same reason that we would want to work in frequency space in the continuous domain, or in S space if we're working with Laplace. And that is that when we have systems, and whether that system is a filter or some physical system with a differential equation that represents it, whatever that system is, when we have systems in the time domain, the effects of systems upon one another are convolving effects. So if we have a transfer function, or if we have a system that has some impulse response h, the only way to find out how that interacts with an input is to take the convolution. Whereas if we work in the transform domain, convolution becomes multiplication. So if we have a process or a filter or a system that we can represent with a transfer function h of z, then h of z can simply be expressed as the output over the input, or more significantly, the output could be expressed as the transfer function multiplied by the input. So that's very convenient because that's multiplication as opposed to a convolution integral. So there's a strong reason to want to work in the z domain when we work with filter design. So let's look at what a very, very simple linear system might look like. And in this particular case, this is taken from your textbook, but it's kind of a bad example because we're mixing n space and z space, which really technically you should never do. Once you express something in the z domain, you always want everything to be in the z domain. But I think what the author's trying to illustrate is that if we take some data set x of n and we input that into a one-term filter, what actually will come out of that is a time-shifted. The output will actually be the input delayed by 1 unit. So this is just to illustrate the effects of a filter. So in the n domain, this really just produces an output that's the input delayed by 1 unit. So some systems where the output is a function of the history of the inputs can be conveniently represented like this. And often we do in linear analysis represent the state of a system as the sum of a set of delayed inputs. Okay, so in the previous slide our transfer function h of z was applied to give a relationship between the input and the output, and so that enables us to use the time shifting property. So this is really just a derivation of going from z space to n space for that particular filter that we showed in the previous example. So as we said before, in this equation, in this first equation, let me grab a pen and let's do something besides red. In this first equation, y of z is our output and x of z is our input. So h would be the ratio of output to input, also known as the transfer function. And so because we're in z space, we take the input, we multiply it by the transfer function, we get the output. Now in this particular example, our transfer function h was z to the minus 1. So just substituting in this line z to the minus 1 for h. And x sub z here is really the z transform of x of n. So in this next line we've just substituted taking z to the minus 1 x sub z and substituting that is basically z to the minus 1 times the transform of x of n. And the reason to do that is that when we get it into this shape, we can apply this time shifting property and thus express it in this form. So we've basically taken, this is that z to the minus k, and where k is 1, and we basically taken that into the time domain, representing it as a time shift. So this line is just a substitution, and then remember that was equal to the output. So now what we want to do is take this entire equation and take its inverse transform Since y of z is just a function in z space, when we take its transform, it's y of n. Since this is the z transform, the inverse transform of the z transform, this gives you the function back. So this just represents what we schematically illustrated already, that a filter of z to the minus 1, transfer function z to the minus 1, has the effect of the output being delayed values of the input.